All right, we are back. Thank you everyone for joining us. This is Astronomy on Tap number 36. My name is Michael Roderick, and together with Arvind Gupta and Jacob Lunn, we run Astronomy on Tap State College. We are going international this time with Dr. Willis Monroe from all the way from Canada, University of British Columbia, and we also have graduate student Michael Palumbo. So two very interesting talks coming up later. Our setup, if this is your first time, if you missed our first virtual Astronomy on Tap, we're going to do a quick how to make an astronomy themed drink with Jacob Lunn. Then we'll cut to our first talk by Dr. Willis Monroe. After that, we'll have trivia with Arvind Gupta, astronomy in the news with Jacob, and then we'll come back to our second talk with Michael Palumbo. So I'm going to go ahead and hand this off to Jacob and show us how to make a super cool astronomy cocktail. Go ahead, Jacob.
All right, so hopefully you saw the ingredients ahead of time. If not, maybe save this recipe for another night or something. But tonight we're going to be making an adaptation of the classic Dark and Stormy. But this, we're going to use an IPA as well, the space dust. So if you have a pint glass, make sure you grab your pint glass. And we're going to start off with our, as I said, the Elysian Space Dust IPA. And if you take your nice Central Pennsylvania Observer's bottle opener, you can open that right up. And so we're only going to use half of this, so 6 ounces. I'm just going to do it by eye. But if you have a measuring cup, you can do that as well. And so I'm just going to take about 6 ounces here. And it doesn't have to be exact, maybe a little more. That seems good. All right, and then the other half of a classic Dark and Stormy is a ginger beer. And again, we're going to take half of that, just about 6 ounces. And I haven't explained it yet, but we're calling this one the Dark and Spacey because of the Space Dust IPA. So this should fill up your glass mostly to the top. That seems about good, maybe a little more. And now comes the dark part of our Dark and Stormy. And that is the dark rum. And I'm told that Gosling's is the brand to use when making a Dark and Stormy. So I'm doing it right, I guess. And you just add that to the top. And then comes my favorite part. I'm a big fan of lime, so we're going to add in some juice of half of a lime. Just take your lime. I've given this a good squeeze already before cutting it. And I like having my fancy little kitchen instrument, so just squeeze that right in there. Make sure you get all the juice out of it. Nice and juicy. And then we're going to top with ice cubes, which I've stored in the freezer. Keep it nice and cold. Uh-oh, I've stored them too well in the freezer. They stuck to the bowl. There we go. A few ice cubes to top it off. And then for a garnish, we're just going to take that lime that we still have, cut a little wedge, and cut out of it to garnish. And there is our Dark and Spacey with Space Dust IPA. Cheers, Michael. Uh-oh.
There we go. Now everyone can hear me speak. But yeah, you mix alcohol like liquor and beer together. At what point can you drink this with a straw? Like, if it has beer in it, does that work? I don't know.
That's an excellent question, and I don't think I know the answer to that. There's probably somebody who has a better sense for that than I do. But yeah, so I also wanted to, while we're here, just quickly talk about space dust and just what is space dust, you might wonder. So space dust is not like the dust that we see, in our homes every day, but these are really, really small particles that are anywhere from molecule size to a tenth of a millimeter. So these are really small particles. And so you can think about that as you're drinking your space dust. And some of these dust particles eventually clump together around the disk of a star and form the little planetesimals that eventually become things like the Earth and Jupiter. So I think that's pretty cool. And think about that while you have your dark and spacey.
Awesome. Thank you. All right.
Yep.
Now that we have our drink set up, we can go ahead and get started. So our first talk of the evening is going to be Dr. Willis Monroe, and he's going to be telling us about what it was like to be an ancient Babylonian astronomer. So go ahead and take it away, Dr. Monroe.
Okay, can you see all right?
Yep.
Okay, well, thank you very much. This is a lot of fun. And I have to say, it's way more fun to watch like a drink mixing tutorial than just wait for like the talk before you at a conference when you're sitting in the audience. If only that could be every conference. So I'm going to be talking today about probably a little bit of a different topic. We're going to look at kind of a little bit the history, the kind of methods and theories that went on in kind of the astronomy astrology of Mesopotamia. So I like to give just a little kind of outline so people know what to expect. We'll start by setting the scene. Where and when are we talking about? This is something you've probably heard about Mesopotamia. Kind of put us all on the same page so we can move forward from there. Next, I'm going to get into kind of the nitty-gritty of what did an astronomer, astrologer do every day. So they practiced observations, they made reports, they compiled texts. And from there, we're going to kind of do a deeper dive into various aspects of being an astronomer astrologer. How did you actually become one? What was the job training like? How did you deal with your colleagues, right? We all have colleagues in whatever fields we're in, and they had colleagues and they dealt with them in different ways, and sometimes they were difficult. And then finally, kind of the perhaps more complex and interesting stuff is the methods and techniques of astronomy in the sort of Babylonian period and text. So what were the complex things that they were actually doing? So to begin with, I've got a water now, I'll have a beer later. But to begin, we're in Mesopotamia. And you've probably seen a map like this before. This is an ancient name for an area that was roughly modern day Iraq and Syria, bits of Turkey and Iran, depending on the period. It has all sorts of names: cradle of civilization, fertile crescent. You've probably heard these things before. But for our purposes, it's kind of important to remember that this was really the area where writing was invented around 3200 BC, so over 5,000 years ago. Sort of large-scale agriculture and some of the first urban cities. Kind of these big collections of people all living together and working together. And we have in various ways and in various capacities, we have astronomical data from about 2000 BC onwards, which is a really long time. It's pretty spotty near the beginning, but as time progresses, it begins to become more detailed and more useful for our purposes. But astronomy has a long history in Mesopotamia, so I hope we'll be able to cover a little bit of that today. But before I get into too much else, I want to just begin by addressing this issue of cosmology. So we all have cosmologies, sort of our understanding of where the world sort of originates or comes from. If you come from sort of a Christian tradition, you're aware of Genesis and how the Christian God creates the world. And Mesopotamians had many cosmologies. This is just one particular one called the Enuma Elish, which is a real foundational one used by the Babylonians. And it includes some really interesting things that I think are worth thinking about as we sort of move forward. This text is very long and complicated and fascinating for all of its parallels, but there's two major things I want to cover here. This is a small segment of it. Number one, you can see that this god Marduk, he appoints the year. He marks off its divisions and he sets up the stars for the 12 months. So initially there's this conception that the stars themselves, the celestial sphere actually tells time, right? And they know how it does because the gods made it like that. And then in the second half of this short excerpt, there's a really interesting section where the god creates the moon. And of course, entrusts the moon to the night. That's not too surprising. But then he also tells the moon to fix the days and do this process month by month, where you begin with as just horns, so the crescent moon, and then you on the 7th day you become half size, and on the 15th day, halfway through the month, you actually stand in opposition with the sun. And if you're familiar of lunar phases, this should be very familiar, where the full moon rises as the sun sets, right? And so the sun and moon are standing in opposition. And then what's kind of, I think is very interesting from this text, is that it says at the very bottom here, it says, when Shamash, the sun, sees you on the horizon, diminish in all the proper stages and shine backwards. It's almost procedural in a way, right? That, you know, what we think of this as this very mythological text, you know, akin to Genesis in the Bible, is actually describing the phases of the moon and giving them in almost a procedural way, where it says you do these things in this order, and then when you reach the halfway point, you do them in reverse order, and then you're back to square one. So I just use this as a way to think about the kind of astronomical knowledge that we might find embedded in other places. You don't always think that astronomical knowledge could be found in mythology, but in certain cases, at least in the Mesopotamian case, there's some rather, you know, you could say, at least for mythology, some complex ideas about astronomy embedded in the text. And I can't proceed from there without including this little clip of The Onion, one of my favorite articles. Sumerians look on in confusion as God creates the world. Good kind of comparative historiography for you. I encourage you to read the article. You can find it if you Google it. But there are two major periods and areas that I want to talk about when we're dealing with astronomy and astrology in Mesopotamia. The first is the Neo-Assyrian court. This is the Neo-Assyrian Empire, where it was an empire centered in northern Iraq, northern Mesopotamia. It controlled much of the Middle East for the first half of the first millennium BCE. And it has kings that you're probably familiar with from reading historical works: Sargon, Sennacherib, Esarhaddon, Ashurbanipal. We're talking roughly 900 to 612 BCE. 612 is when the empire falls. But for the purposes of the talk today, what's really interesting is that these kings were fascinated by the messages contained within the heavens, right? And so they employed this huge network of scholars who would basically give them advice on all sorts of things. They would ask questions, they would receive feedback, and aspects of divination, so astrology in particular, factored really heavily into their decision making. And so these were the scholars who were watching the sky, interpreting everything, and starting to actually develop theories of astronomical kind of data collection and data prediction, all so that they could provide the king with information. And these scholars were employed, of course, you know, as in any sort of empire system, they're employed at the will of the king, right? And often they were out of work if they displeased the king. So that's the Neo-Assyrian period, the first half of the first millennium BCE, and we're going to look at some of that material in a second. The other major period that we'll look at is what I'm terming roughly Hellenistic Babylonia, but essentially the latter half of the first millennium. So a few hundred years after the Neo-Assyrian period, there's this other flourishing of scholarly material and astronomical practice. And this is taking place around the cities of Babylon and Uruk in the south of modern-day Baghdad, between the years of 400 to 100 BCE. And these are astronomers and astrologers. They're no longer advising the kings. The kings at this point are foreign, they're Persian, they're Greek. Alexander the Great, for instance, is one of the kings, Darius, Cyrus, Xerxes. So these Babylonian scholars are no longer working with these kings. Instead, they're situated in the temples, and they're almost like kind of like tenured professors. They're just doing their work, right? They're conducting research, developing new methods. They're doing some administrative stuff on the side, like figuring out the calendar, but for the most part, they're developing really interesting theories of planetary motion. This is also the period when the zodiac is invented. So the zodiac signs that we're familiar with from our sort of horoscopes in the newspaper come from the Babylonian system, which is invented around 400 BC. So let's start looking at what these astronomers actually did. So the first thing that was kind of important was observing the sky. You know, with any sort of theory of astronomy, you have to start with observation. And both in the Neo-Assyrian period and in the Hellenistic period, the astronomers watched the sky for whatever was happening. And they watched the sky and they recorded it. Later on, we're going to talk a little bit about this later, the astronomical diaries, which I noticed were in your intro slides, which is great. So the native term for these is called Natsaru Shagine, which means regular watching. And Natsaru, actually, the verb has to do with guarding and watching. So you can imagine that there's this kind of feeling of the astronomers of watching the sky and being ready for anything, right? They have to make sure they can see everything that's going on. So by doing this regular watching, by doing this observation, they recorded a lot of information. And they have this very long sort of record of observational kind of information about planets, about the moon and sun, about various stars. And the other thing is they would also use water clocks to take sort of more accurate measurements. So, you know, tracing the rising of various stars across the horizon, they would measure the intervals between different important stars by using a water clock to get kind of more accurate data. So the image you see on I think it's the right of your screen, maybe the right, on one side of your screen, the image is actually of one of these astronomical diaries, so these compilations of observations. And this one, to show you how kind of disinterested in a way these scholars were, they're recording all of the information that's happening, you know, night by night during a certain month. And they say the night of the 29th, the king died, there were clouds. Well, that king happens to be Alexander the Great, right? This is our contemporary record, our contemporaneous record of Alexander the Great's death in Babylon. But the astronomers just said, well, the king died. Also, by the way, it was cloudy. And so we couldn't make observations. So they were kind of working, they were interested in what they saw in the sky. So the scholars from both the Neo-Assyrian period and the Hellenistic period were watching the sky all the time. And what did they do when they saw things? Well, they compiled reports. This should be very familiar, right? We look at things, we write reports, and we file them. And at least in the Neo-Assyrian period, these reports went straight to the king. So they would see something in the sky, and they would write it down, and they would send a quick letter. And the tablet you see here is quite small, actually. And I should just quickly explain. This is the front view you see on the top, the edge view in the middle, and the bottom view on the back. So it's this little clay object, you know, maybe not much bigger than a stick of gum. It's pretty small. So I've given the text of this tablet on the left on the screen here. It says, the night of the second day, Jupiter stood in the halo of the moon. Let them perform a Namborbi ritual. The halo was not a closed one, from Nabu Ahe Iriba. So Nabu Ahe Iriba is a well-known astronomer from the Neo-Assyrian period. He's filing this quick report with his boss, the king. He's letting him know that in this month, it's inferred from the date that it was sent on the second day, Jupiter was near the moon, and it was perhaps, yeah, within the halo of the moon, but the halo wasn't closed, and that was auspicious. And so they should perform what's called a Namborbi, which is a ritual to make the evil go away. So this is kind of interesting because it kind of melds astronomy and astrology, and this is a theme throughout. There were no separate terms in Mesopotamia for either of these things. Both of them were considered really the same art. You would predict the sky, watch the sky, and then you would also interpret what happened in the sky. Because remember, these things were all created by the gods. Messages were sent by the stars. But here you can see that they're able to recognize planets in the sky, note that when they're near certain other celestial objects, and make those reports. Often there were clouds, of course, and they note that. They say, we couldn't see anything, it was cloudy. And that in itself is a report. So you observed the sky, you wrote reports. What else would you do? Well, you can't do much observation during the day. And so that's when you would, before I get there, this is a fun little thing I wanted to share. This is another report from a scholar about certain things happening. There's the moon and the sun are seen together at the middle of the month. That's expected. So it's a good omen. But then at the second half of this text, you see it says, let them bring the Paliptych, the multiple tablet series of Enuma Anu Enlil, which is a big astrological handbook. And they want the king to look at it. And then they want to draw a picture for him. So you can imagine appealing to your boss, right? You file a report and you want to prove that you were right. And you say, well, let me draw it out for you, right? And we actually know what these drawings look like. So here's a quick little snapshot. These are circular astrolabe, circular star charts. And we have a couple preserved from the Neo-Assyrian period. And this is clearly what they're referring to there. So, you know, some astronomer, remember, they served at the will of the king. You know, he files a report. He wants to prove that his interpretation is correct. He says, I'm going to make sure that, you know, the king understands and keeps me in my job. So I'm going to draw a picture for him. And these are the kinds of things that they would draw. So you've done your observation, you've done your report. What else do you do? Well, during the day, you can't do much observation. So you do paperwork. And this is what they did. So lots and lots of tablets were recopied, copied, brought together, compiled. They would take their observations and make big summative tablets. This tablet that you see on the screen, it's quite fragmentary. All these things are fragmentary. They've come out of the ground after many thousands of years. But this particular tablet actually records collections of eclipses in Saros cycles. So if you're familiar with the Saros cycle, 18-year cycle of eclipses, and every column of this tablet is one entire Saros cycle. So if you move horizontally across it, you get the same type of eclipse separated by 18 years. So it's a really big, actually, it's almost like a kind of big data undertaking for the ancient world, right? Compiling all the eclipses across multiple Saros cycles, hundreds of years. And this is something that scholars would do. They would take all these reports, take all these observations, and they would compile them into new forms of data. So that's kind of the gist of a really basic summary of kind of what they would do day to day. So observe, report, and compile. But how did they get there? Well, they got there by learning to write. They'd go to elementary school. You see the tablet on the left here, the earliest form of scribal education, just pressing single wedges into a clay tablet, practicing your letters. And on the right here, you see lists of planets and stars. And then, so once you've kind of specialized a little bit, you might go into an apprenticeship. And so on the left here, you see a tablet that was written by a father-son duo, a kind of apprenticeship situation. And by the way, this is Leo the lion, one of our earliest depictions of the zodiac sign, on the back of Hydra, the constellation. And then on the right here, you see this is a really nice article. It's a little excerpt from a figure in an article by Matthieu Ossendriver. And it shows just the really dense networks of scholars working in the latter periods. These are father-son relationships. These are colleague relationships. They're all working with each other. You're a junior scribe. You train with a senior scribe until you master your craft. And then how do you deal with these colleagues you might have, right? So there's just a couple humorous examples I have here, which are kind of fun. Sometimes you disagree on what you've seen in the sky. I'm sure that's never happened to anyone before looking through a telescope. But sometimes you might look at something and you're not quite sure, and your friend's not quite sure either. And so you kind of get together and figure out what it was. And so this is a letter to the Neo-Assyrian king, again, from some astronomers, who said that these two astronomers, Nabu-Ahe-Eriba was the one we saw before. So here he is again. They disagreed about something. That night, they went out, they looked again, and they were satisfied that they came to an agreement, right? So if you disagree, you go out at night and you check together, and then you come to an agreement. But sometimes that doesn't work. Sometimes you have colleagues who are just not very good at astronomy. And so this is another letter, again, and this is from the astronomer Balassi to the Neo-Assyrian king. And he's berating one of his colleagues, who he says really can't tell the difference between Venus and Mercury. So apparently this astronomer wrote to the king and said, oh, Venus is visible. You should be careful. Like, this means something. And Balassi says, that guy's an ignoramus. He doesn't know the synodic, right? So Balassi is referring to his own astronomical knowledge of the synodic cycles of Venus, right? He knows when Venus should be visible. He knows it's not visible. And he says he can't believe, who is this guy who confuses Venus and Mercury in the sky? So dealing with colleagues can be sometimes quite difficult. People had different levels of knowledge. Okay, so I see my time is growing short. So now let's get on to methods and techniques so that we can kind of dive a little bit deeper into some of the more complex things they were doing. So what was astronomy even good for, right? Well, it was very good for protecting the king, protecting the land, interpreting signs in the sky. But how did you actually use it on the ground? What was sort of the nitty-gritty techniques involved in the astronomical craft? The first one is really basic, calendrics. Astronomy is very, very useful for telling time. Of course, things happen in regular sequences in the sky. You can watch for them, you can wait for them, and then you can sync things up. They had a lunar solar calendar. So they had a lunar calendar and a solar calendar. Of course, they get out of whack. So they had to fix them pretty often through processes of intercalation, and watching for things in the sky was one of those processes. The tablet you see here is a really simple example of the visibility of the moon increasing and decreasing over one calendar month or lunar month around the winter solstice. And so let's see if I go back, if I do my pointer, you can see that the numbers here, if you can read the cuneiform numbers, they're relatively simple. They're increasing. So you see the ones here goes to twos, goes to threes, goes to four, and then goes from threes, and then goes back down to twos. And there's numbers afterwards as well. So a really simple function that just shows the increase in lunar visibility throughout the lunar month, and then the decrease after the full moon. But there are two main kind of developments in the late period that are interesting. They're called non-mathematical and mathematical astronomy. So non-mathematical astronomy is essentially using observations to predict future observations. And this is where the astronomical diaries come from. These are day-by-day or night-by-night accounts of observations, including some predictions. There are these things called goal year texts and these things called almanacs, and they all work together. Basically, the diaries provide the data for the goal year texts, which provide the data for the almanacs, and the almanacs fill in the gaps for the diaries when you can't observe. So basically, by using previous observations, you can predict future observations. So really simple, just kind of phenomenon. The diaries themselves are fascinating. They include a lot of really interesting information, and this is kind of what was hinted at in the intro slide for the talk, that these diaries provide us with a wealth of astronomical information to pull from. So length of the lunar month, so whether it's 29 or 28 days, the lunar 6, which are time measurements right around the first day, last day, and the full moon, the positions of the moon, the planets, all sorts of other information. And interestingly, also, they have information about prices of commodities, historical events, river levels. And this is because the Babylonians kind of thought that if you capture enough data, you can start to predict these cycles, right? Even if it's not the sky, you can look at other things. But the kind of more interesting stuff was the mathematical astronomy. And this is where Babylonian astronomy starts to get very complex. And I'll even show you something at the end, which is kind of new data. So the most famous examples of these are what are called the ephemerides, and these were studied in detail by Otto Neugebauer, the big historian of astronomy. And these are just tables of numbers. They're calculated synodic events. So they're looking at the regular repetition of certain types of things. So Jupiter's last visibility in the sky, for instance. And they calculate how much time is in between each of these events. So they have two major functions for looking at this. They have step functions, which are called system A, and zigzag functions called system B. And so if you see in this slide, I've just given you some examples of Jupiter in system A, so the step function. And basically, the idea is that Jupiter, from a geocentric perspective, its velocity changes throughout its cycle. So if we're looking at Jupiter, it speeds up and slows down in the sky. And they have multiple systems for this. So they have system A, there's system A prime, and it just varies how many steps they have, basically the speed at which it goes. And so this particular procedure only has two speeds. So Jupiter goes at one speed through most of the zodiac and at another speed through the rest. And what's really interesting is when you get at the middle point, you have to figure out a way to average the speed. And this is why essentially what they're trying to do is they're trying to replicate a wave function, right? This is a constant change in velocity for the planets. And so they created this step function, which has two different speeds. And when you move between the steps, you actually have to kind of average your velocity to try to get closer. And then, like I said, they would add more and more steps to make these things more and more accurate. The other major function they would use is the zigzag function. And this is just a maximum and minimum. You proceed with a regular difference throughout the cycle. So again, you can sort of calculate this change in velocity over time, getting closer to this wave function. So these are the two major kind of big developments in the Hellenistic period, in the latter part. So 400 BC onwards is creating these really complex systems for predicting where the planets appear in the sky. So the last visibilities, the retrograde motion, stationary points, etc. And I'll just end with kind of this. This is brand new, at least in the scheme of history of astronomy and history of Mesopotamian astronomy. Brand new data from 2016. A scholar named Matthieu Ostendreiber, who's a really brilliant colleague over in Germany, published this article in Science where he showed that they actually calculated the area under sort of under a graph for looking at this change of velocity. So almost like a proto-calculus. So really cool stuff. So I'll just sum up with a quick afterword. Looking at this material, it's really remarkable to see the kind of longevity of these observations and methods and how they were used later on in history. So Ptolemy, for instance, uses them. They make their way into Indian astronomy, which is really cool. And they really give us remarkable insight into scientific thinking, the complexity of scientific thinking in Mesopotamia. And finally, I think the social aspects, like the dealing with colleagues and learning how you become an astronomer, really give us some sort of humanity to these ancient Mesopotamians, and sort of how they also experienced looking at the sky. And I'll just point to these two books. One is by John Steele, A Brief Introduction to Astronomy in the Middle East, and the other by Francesca Rochberg, The Heavenly Writing. They're both excellent, really good introductions to the field. So if you're interested in reading more, I recommend both. So thank you very much.
Awesome. Well, thank you very much. We have been waiting a while to get a kind of history of astronomy talk for our series. So I'm really, really happy that you're able give that talk for us. And for the people watching online, if you have any questions, please type them into the chat. So we have one question here from Angel. How many of these tablets, do we have an idea for how many of these tablets with astronomical observations have survived to modern day? Like how many have we lost? Do we have an idea?
Yeah, that's a great question. So you probably noticed that a lot of the tablets don't look great. They look pretty broken, and very few are perfectly preserved. But I'd say we've got good couple thousand astronomical tablets preserved. Now, it should be said that not all of these are studied. Many are sitting in museums with no one to look at them. It's my job and my colleagues' job to kind of go around and find them and work on them. And more are coming out of there are plenty more still buried in Iraq, and we should definitely work towards sustainable and ethical excavation of material from Iraq to bring this kind of really remarkable history to light. But there's still a lot out there, and there's still a lot undiscovered. As you saw in that last thing I highlighted, even in 2016, we're discovering new methods that they've created for calculating this stuff.
Would this knowledge have been considered lost, or did it kind of continue? Was this knowledge passed on from generation to generation, even like down to today?
That's a good question. So I hinted at the end that some of this made it into Ptolemy and sort of Greek astronomy, and then some of it made it into Indian astronomy as well. There are small things, especially like astronomical constants, like the length of a synodic lunar month or something, that we find transmitted all the way, right? But a lot of the more complex methods did unfortunately get lost. They were long dead. And then they were rediscovered basically end of the 19th century by some German Assyriologists, people who studied this material. And then it was Otto Neugebauer who really kind of kickstarted the revival of understanding this stuff.
Okay. We got a question here from Hamid. What about Babylon's neighbors, for example, Elamites? Did they have any similar knowledge to the Babylonians?
Yeah, that's a good question. So not really. I'd say when we're looking for comparative information, especially for the Hellenistic period, there's some astronomy going on in Egypt. Not as much. They were much more concerned with basically cataloging Sirius, the star, and its kind of synodic phenomena, and then obviously in Greece. But the problem with what's happening, problem with all of this history stuff, as a general statement, is it really depends on the survival of evidence. And we are super fortunate that for Mesopotamia, they chose to write on clay, and that clay got buried in the ground, turned basically into stone, give or take a couple, hard to scale things, and survives to the present day. What's happening around, maybe about 500 BC onwards, is that there's a real movement to write in Aramaic and to write in ink on parchment. And so we don't know what we've lost. There's probably huge amounts of astronomical knowledge that was written on parchment, put into clay jars. Those clay jars got moldy, the parchment rotted away, and we've lost everything. The clay tablets survive, so we have those at least. But we have hints. A lot of the tablets actually have little notes at the bottom, like we call them a colophon. It's basically who wrote it, why they wrote it, where they wrote it, stuff like that. Many of them say they were copied from wax tablets, and those wax tablets don't survive. So there may be much more information that has long been lost, even in Mesopotamia and then in neighboring cultures where they didn't write on clay.
Okay. Did the astronomers have any motivation to lie about the observations that they saw to kind of, oh yeah, this is a really good thing. That's good that there's a solar eclipse kind of thing. Or...
Yeah, that's a really good question. So I'd say they definitely did have motivation. Whether or not they could follow through without getting caught is another matter. The kings, as you can imagine, were very savvy, and they had multiple observers in multiple places, right? And these people weren't necessarily talking to each other, so they would receive multiple reports. And if one person's consistently standing out against the crowd saying, oh yeah, don't worry, solar eclipse, definitely a good thing, then they might not keep them employed anymore. I should also say that there's other forms of divination, and these other forms of divination could be used to check. So you might see something in the sky, and then you might sacrifice a goat and read its liver. and that would be a way that you'd figure out whether the thing you saw in the sky was true or not, basically.
Would it be like a, you're fired, or a like we're taking off your head kind of thing?
That's a good question. We don't have any evidence of astronomers or astrologers being outright killed on their job, but we do have these really kind of sad letters where they're begging for their jobs, and they basically list their CV, right? They say like, I'm an expert in all these texts. I know X from Y from Z. I trained with all these people. Can I please have a job? And they use all this language of like groveling at their feet and being dogs and stuff like that, just begging for employment from the king.
So not much different from today, then.
Exactly, right. It's a cover letter all over again or something. Yeah. Yeah.
All right, we got a question here from Rubens. Did they inherit some constellation names from even older traditions?
Yeah, that's interesting. So in terms of the names of the constellations and stars, when we're talking about the linguistic milieu of Mesopotamia, you're talking about the writing system cuneiform, but two major languages: Akkadian, which is Semitic like Hebrew and Arabic, which is by far the most common from about 2000 BC onwards, but also Sumerian, which is the earliest known language, and what cuneiform was kind of invented to write. Perhaps it's somewhat controversial. The names for the constellations are often written in Sumerian, but have Akkadian equivalents, kind of like a translation, glosses or something. And so there's evidence that some of these are pre-Akkadian. They might be Sumerian inventions. In terms of coming from other places, we're not really sure. But if you had to say any sort of origin for the constellation names, I think you would say they came from basically Sumerian language. So, sometime during the 3rd millennium BCE.
Okay. All right. Very cool talk. Really appreciate you coming out to us virtually all the way from Canada. Thank you again so much. And,
yeah, my pleasure.
Good luck in your work.
I'll enjoy I got Galactic Space Dragon beer, so I'll enjoy my beer now. So, thank you very much.
Thank you. All right, we are ready now for trivia. So we're going to hand this over to Arvind Gupta, who's going to take over for us. Go ahead.
Give me 1 second here. Sorry, I'm dealing with computer issues, but we'll have it in a sec.
All right. We can reflect on the talk that we just heard. Think of how cool that was.
Are you guys seeing a screen?
Right now it says Arvind Gupta has started screen sharing, but we don't have the screen just yet. However, my internet may be slow. If you want to try that one more time.
Yeah. Oh, here it is. You got it?
We're good.
Okay, cool. Thanks. Yeah, sorry. I'm using a friend's computer right now because my webcam is not working properly. But there we go. Okay, so first, yeah, thanks, Willis, for such a great talk. That was really interesting. That's something we've been wanting to hear about for a while, like Michael said. So now let's go on to trivia. So for those of you who aren't regulars for our event, those who haven't been coming in every week, both in person before we started isolating and either to our event last month, the way trivia works is that I'm going to ask you guys a series of 15 questions that are themed. Tonight's theme, if you can see here, is what's that wavelength? So I'll ask you a question. I'll show you an image of some astronomical object, and then you have to tell me which wavelength that image was observed in. So what we were using to take the picture with our telescopes. The way trivia works is if you go to this hyperlink right here, tinyurl.com/AOTSC36, it'll be a Google form where you answer each of the questions as I go through these slides here. There's also the first question there will ask you for your team name, and that will be used as a tiebreaker. So whichever team has the most creative astronomy themed name will be the winner of tonight's trivia if there's a tie for the most points when we get to the end. I'm going to go through each of the questions 2 times, so I'm going to go through all of them once, and we'll do a really quick brief review after we're done with that. After that, we will move on to astronomy in the news with Jacob, and we want you to have all your answers submitted by the end of astronomy in the news. So once trivia is done, you'll have 3 to 5 minutes while you're listening to Jacob to wrap up and finish submitting your answers. We also ask you to put your email into that Google form if you're interested in receiving a prize, if you're the winner. As prizes, we have a few nice little things. So we have a beer koozie from Astronomy on Tap State College. We also have a Central Pennsylvania Observer's bottle opener, the one that Jacob showed earlier. And we have some nice Astronomy on Tap magnets. So without anything else, let's go
Just to say, quick interrupt real quick. We do have the link in the chat, so if you want to go ahead and click on that, you can get to the trivia forum. All right, that's all.
Thanks, Michael. Okay. So for those of you who aren't familiar, the electromagnetic spectrum it's pretty much, it describes how light is split up across all the different wavelengths. When we talk about ultraviolet light, infrared light, radio waves, gamma rays, and cosmic rays, these are all different parts of the electromagnetic spectrum. And if you're going through these trivia questions over the next few slides, you'll see that all the options are all listed on the left here. And if you don't quite remember what wavelength each of these options corresponds to, this XKCD comic is a nice little reference for you to go to. As an example of one of our questions, if I showed you this picture of Mars, the correct answer would be that this was taken at visible wavelengths. There's a fun twist, though, that I've added, because a lot of the people in the audience are astronomers, and they've seen a lot of these images before, and they kind of have a nice intuition for what colors correspond to certain wavelengths when we use false color images. So for some of these, I've recolored them to make it a little bit harder for those who are astronomers and have a better idea of what's going on. So question number 1, this is an image of the Crab pulsar. So that's this little star in the center here. It's in the middle of the Crab Nebula, which is the whole thing. The Crab pulsar is it's a remnant of a supernova that went off in the year 1054 that was actually observed all across the globe. It's one of the earliest recorded sightings of a supernova from Earth. And this pulsar here is what that star ended up becoming after the supernova went off and completed. For number 2, we have another supernova. This is supernova 1987A. This one went off in actually one of the Magellanic Clouds. So it's the closest supernova to Earth to go off in the modern era, which is really cool because when it was first observed and noticed back in 1987, astronomers were able to sort of observe it unfolding in real time, see the expansion of all the gas from the supernova, and see how supernovae observed on a much better scale than we're able to do with things that are much further away. Number 3, this is the black hole in the center of the elliptical galaxy M87. This is a very recent image. There was actually a lot of press about this when it was first released a few years ago because it is the first and highest quality image of a black hole that we have. I know it doesn't look very high quality, but the fact that we have this at all is actually incredibly impressive, and a lot of really cool science came out of this. Number 4 is the Cat's Eye Nebula. This is actually something that people have very often seen images of, but most images of this nebula are just focused on this little central piece right here. I'm showing a more zoomed out version, which shows a lot of what I think are interesting further out regions of the gas from the nebula. Number 5 is the Andromeda Galaxy. So this is the closest large spiral galaxy to the Milky Way. We're on a collision course with this guy in something like 4.5 or 5 billion years, which is, I think, also the time that the sun is supposed to run out of fuel and enter its giant phase. So if humans are still around 5 billion years from now, we're going to be dealing with a lot of interesting astronomical doomsday phenomena. Hopefully we are still around, but also maybe it would be nice if we aren't. Number 6, this is an image, or actually an animation of Venus. I think one of the coolest astronomy animations, in my opinion, that we're actually able to have this visualization of a rotating, of a full 3D view of a planet that is not, it's not even a very recent image. So our technology, when this was taken, I'm not going to say when it was pretty impressive, but yeah. Number 7, so I'm sure a lot of you have been following the path of the comet Neowise over the last few weeks. This was one of the first and brightest naked eye comets in the last few decades, I think. Sorry, Neowise was, not Halley's Comet, but Neowise was really cool to see. That was actually the first naked eye comet that I have seen. But it wasn't nearly as impressive as something like Halley's Comet will be the next time it returns to Earth. This is an image of Jupiter's aurora. I'm not sure if I can give away too many fun facts about this guy without telling you guys what the answer is. Yeah, I don't know. Number 9, an image of 2 galaxies called NGC 3808A and B. I think the one on the left is A and the one on the right is B, but I could be entirely wrong about that. And these are 2 galaxies that are in the middle of a merger. So they are stripping stars and gas from each other, and they will relatively soon, not on human timescales, but on astronomical timescales, they will merge into a single galaxy. So this isn't something that we can expect to observe in real time from Earth, but relative to how soon we're going to merge with the Andromeda Galaxy, these guys are pretty much on the brink of colliding. Here's another image of Venus. Actually, it's not my favorite planet, but somehow it got in here for 2 slides. One clue about this that I will give is that this was not taken at the same wavelengths as the other Venus image. That might seem really obvious based on how different the 2 are, but you'd be surprised about how different extraction techniques can make really cool different images. Here's the Cat's Paw Nebula, not the same as the Cat's Eye Nebula. I don't know, I think Michael suggested both of these for the trivia. I'm not sure why he likes cats so much. He strikes me more of a dog guy. HL Tauri, so this is a protoplanetary disk of a T Tauri star. So young star that's still forming. And you can see all these ring-like features here are, these are gas and dust that are orbiting the central star, which is in the center here. And these are things that will eventually very likely turn into a planetary system around this star, much like the solar system in our own, around our own sun. This is NGC 6744, a nice spiral galaxy that it's one of the galaxies that gives us a nice idea of what our own Milky Way looks like, given that we can't really see what our galaxy looks like from the outside. So we have to use images of other spiral galaxies like this one to sort of infer what the structure of our own is. Here's another animation. This is an animation of the impact of Comet Shoemaker-Levy on Jupiter. So right here in the center, this big guy is Jupiter. On the right, we have Jupiter's moon Io. And then on the lower left here, you'll see a sort of bright impact. And that is this Comet Shoemaker-Levy, that collided with Jupiter, I want to say in the early 90s, but it was before I was born, that's all I know. But yeah, it was really cool that we're actually able to capture this sort of impact with observations. Number 15, this is the last question. This is an image of the sun. It shouldn't look like what you would see with your naked eye. Also, please don't look at the sun with your naked eye. Use eclipse glasses, use a solar telescope, use something safe, but also we can see a lot of prominent features on the sun that we don't normally see. We normally see the sun as mostly a featureless disk. But if we look at it in other wavelengths, we can highlight some other really cool things. So I'm going to rewind now all the way back to the beginning and then go through all of these guys one more time. I'll spend about 15, 20 seconds on each. I'm not going to go through the facts again, but this is just to help you remind yourself of what they are as you go through the trivia answers. Okay, so we are back at our last image. I will make one quick clarification here. There are some that are maybe closer to the microwave than the radio, but for these purposes, because they're kind of borderline, I've lumped microwave and radio into a single category. So anything that's longer wavelength than infrared, the correct answer would be radio wavelengths. So hopefully that didn't cause any confusion, and if you were confused before, hopefully that clarification helps. So we are about to move on to astronomy in the news. So I will stop sharing and hand it off to Michael and Jacob. And after this is done, we will give you another just a few minutes. So the end of astronomy in the news is when you have to have your answers in. And I'll announce the winner at the end of the second talk.
All right, thank you. I feel like we may have ostracized the millimeter community with that comment, but there's not many of them anyway, so we're okay. All right, Jacob, what is going on with astronomy today?
Yeah, so Iron stole my thunder a little bit, but presumably people have already been seeing a lot or heard a lot about comet Neowise in the news. It's sort of been the big topic. It's stretching out beyond just astronomy community, but to kind of everybody, because it's a nice object you can see in the sky and doesn't happen very often. But yes, as Arvin said, this is comet Neowise. So I'm just showing a few pictures here. The two on the left are actually ones that I've taken. So that was kind of cool. Like Arvin, this was my first naked eye comet that I've ever seen. But yeah, so what is comet Neowise? Well, it was a comet that was discovered back in March of this year. And its name, Neowise, comes actually from a combination of two things. It's named after a project that people are working on at Caltech, and it combines NEO, which is an acronym for Near Earth Object, and WISE, which is a satellite, the Wide Field Infrared Survey. Now I'm forgetting what E is. I think Explorer. I'm going to say Explorer, but I'm forgetting at the moment what exactly that E stands for. But that's where its name comes from. This is an infrared imaging survey that is looking for near-Earth objects, and this is maybe not quite near Earth, but it was found anyway. But if you haven't gotten a chance to see it, it's sort of on its last legs here in the next week or two. Hopefully you've had a chance to go out at night and look. And if you didn't, just set your calendar for 6,800 years from now, because that's its period. This is almost 7,000 year period, and comets are generally on very eccentric orbits, which brings them in really close to the sun, which is why they start looking so bright. They're made up of lots of sort of loosely held ice, gas, and some dust. And then when it comes close to the sun, it warms up and that's ejected. And as Arvin was saying, this is the first bright naked eye comet that's been seen in a long time. So these comets come in fairly regularly, but to be seen on Earth with the naked eye is more rare. I guess the last one to be seen was Comet Lovejoy in 2011, but that was mostly visible when it was visible and close enough to the sun. It was in the southern hemisphere, and again before that was the Hale-Bopp comet in '97. So it's been a while for us northern hemisphere people, especially since I was only 4 when that Hale-Bopp was there. But the other thing that's interesting about comets is they actually have 2 tails. So this picture just shows the blue tail there is the ionized gas that's coming off of it, and that points directly away from the sun. And then the sort of brighter white yellow tail is the dust that's coming off, and it's mostly pointed away from the sun, but then is curved a bit because of the comet's orbit. And so yeah, this is the dust tail, and kind of ties in, with the space dust drink that we made earlier today. And then the last thing I just wanted to say, related to the first talk, there's a really cool Twitter thread by Dr. Moody Al-Rashid, who is looking at similar things to Dr. Monroe, who gave our first talk, and goes through, kind of this good thread on comets in Assyrian and Babylonian times, And I thought it was a really interesting read. And so I encourage you to go check that out if you're interested in thinking about what those people back then were seeing in the night sky, and it's not so different from what we're seeing now. So that's astronomy in the news, and I'll remind you to submit your answers for the trivia by right now, essentially, so that Arvin can go ahead and grade them.
All right, thank you, Jacob. I can remember actually going out to watch Hellbop back when it came out and being very underwhelmed with it because it was propped up to be this really beautiful comet. People were comparing it to Halley's Comet, and no, had to see it through a telescope. But
I'll remind people that these images that I showed are, taken with a camera with long exposure, and so seeing it with your naked eye is maybe much less dramatic. And one of the things that they say to do, if you look at it directly, it's harder to see. But if you kind of find where it is, you can look at it, and then you kind of look just slightly away from it, and so that it's kind of in the just off center of your vision, and then you can see it a little more clearly. And I forgot to mention, there's also an app, a cool app called Comet Neowise that an astronomer put together. Its sole purpose is to tell you where Neowise is. And yeah, so I have it on my phone, but yeah, it's an easy way to find it in the sky.
Awesome, thank you. All right, so submit your trivia answers if you haven't done so already. We're going to start up with our next talk and have the answers after that is finished. So next up is graduate student Michael Palumbo, and he's going to be giving a talk about the science and experiences of Black astronomers. So go ahead, Michael.
Hey, everyone. Oops. Like Michael said, my name is also Michael, and I'm a third-year graduate student in the astronomy department at Penn State, and I'll be talking a little bit about the work and experiences of Black astronomers. So I want to lead by addressing a question you may have already asked yourself by this point, and that question might sound something like, why am I, a white person, giving this talk? And that is a perfectly valid question, and there are a couple of responses I want to give. So issues of race are important to talk about, and it's on all of us to talk about them and to affect change, and not just people of color. And I do want to caveat that as a white person, I haven't had the lived experiences of a Black person, but what I can do is amplify discussion of those experiences and make sure that those voices are centered in conversation in issues or in conversations about race. And then everyone, including me, including you, has the duty to educate yourself and to educate others about issues of racism. And then I also want to say that we'll be talking about issues of racism in academia. And the Penn State Penn State Astronomy and Astrophysics Department, to my knowledge, does not employ any Black astronomers. So that doesn't mean that issues don't exist in our department. That just means that someone who isn't Black will have to say some things about those issues and how they might manifest in departments. So I want to start by touching on the long and nuanced history of how Black folks have contributed to astronomy. Now, this will by no means be comprehensive, but I do want to start with a little introduction. So back in the 1700s, Benjamin Banneker was a free Black man who was actually a self-taught astronomer. And using his self-taught knowledge of astronomy, he published several almanacs in which he detailed the phases of the moon, the motion of the planets, and predicted events like solar eclipses. If you've seen the movie Hidden Figures or read the book it's based on, the names Katherine Johnson and Mary Jackson might be familiar to you. These were Black women aerospace engineers at NASA in the 50s and 60s who were critical in solving the engineering and mathematical problems that needed to be solved to achieve crewed spaceflight and ultimately the moon landing in 1969. And then a name I actually just learned was Mercedes Richards. In the early 2000s, she was a professor in the astronomy department at Penn State, and she was actually a pioneer in the field of Doppler tomography. And like I said, this history is by no means comprehensive. I've linked some other sources, but I don't think you have access to the slideshow, but you can look more into this on Google. But it must be said that in spite of this long and detailed history of contribution by Black astronomers, this contribution has been made despite that Black students and researchers are severely underrepresented in physics and astronomy. And to give you a sense, a numerical sense of how this is, we can look at some pie charts. So here I have a pie chart of the resident population of the United States in 2007. So as intuition would suggest, about 60-some% of the United States population is white, and then about 12-13% is Black. But if we look at another pie chart, which shows the percentage of faculty jobs by race in science and engineering, we can see there's a really different story here. So white men occupy about 60% of those science and engineering faculty jobs, despite the fact they're about 30% of the population. And conversely, Black folks make up about 3% of those jobs, despite the fact they're about 12-13% of the population. So there's a severe underrepresentation here. And if we look at this by subfield, so by science, this gets not much better. So physics is among the least diverse of the sciences. So if we look at this left plot, we're looking at the percentage of bachelor degrees that were earned by Black folks as a function of time. And despite the fact that college-age Black students make up about 14% of degrees earned, in 2017, only about 3% of physics degrees conferred were given to Black folks. And then if we look at a similar story for Black women, we can see that the issue compounds. So we would say that Black women are marginalized with respect to both race and gender. So that's where their axes of identity intersect. We can see that over time, the number of PhDs in physics earned by white women increases with time. So that's good. The field has become more accessible for them. But the same cannot be said for Black and Hispanic women, where we've seen essentially no change over time, no growth. So there's obviously an underlying problem here. And I want to state early and unequivocally that the underlying cause of these problems is racist thought and racist policy. The underrepresentation is not driven by any supposed cultural differences or inferiority, implicit or explicit. The cause of this lack of representation is racist thought and racist policy that exists still in academia, whether knowingly or not. So this is an injustice, and I think a good response to this is shown in this excerpt from the study by Archer et al. In 2015. They say, the absence of Black students from prestigious science routes is a social injustice in itself that needs to be addressed in its own right. So there's a problem here, and we need to address it. It's ethically right to do. So when we begin addressing this problem, one of the analogies we usually initially encounter is this analogy of the leaky pipeline. So the idea here is there's this pipeline that produces scientists. We start out at one end and put in young people like high schoolers who are interested in science and send them through their education and career trajectory. And out the other end, we get scientists. But the analogy goes that this pipeline is leaky, and along the way we lose people. And specifically, we tend to lose marginalized people like women or Black folks. And so this analogy has some use, but it is imperfect, and I do want to highlight some of those imperfections. So the leaky pipeline analogy implies that there's one way into STEM and there's one successful outcome. That outcome is a job in science, and oftentimes we tacitly assume that that successful job is that of a faculty member, so of a professor. It also wrongly assumes that the path to a STEM career starts as early as high school. And that's just really not true. If you were to poll current scientists in developed career stages and asked when they knew they were on their career trajectory or if they were interested in their current job in high school, most of them would say no. Their career paths were probably much more nuanced than that and had some, circumlocution and wandering about. It also wrongly assumes that certain invariant steps must be taken to progress, so that there's this prescribed model. You go to high school, you take these classes, you go to a specific undergraduate institution, major in these prescribed majors, and then apply to grad school. And that's just not the case. Like I said before, people's career paths and educational paths have much more nuance to them. And then this analogy also problematically suggests that if we increase the flow, we'll fix the problem. We'll get out more scientists out the other side. And sure, if we get more young people interested in science, we will probably get more scientists a number of years down the line. But the issue is that doesn't fix the leaky pipeline part. That just means more people will leak out and be subject to those forces that push them out of the field. And that's a harmful thing to do. So that's not necessarily good. So I think a little bit more nuanced model is given by the Australian Academy of Science. So they have this career progression pipeline. And it's imperfect, but I think it does have a bit more detail, which I like. And instead of parameterizing this in terms of successful outcomes, like getting a job in STEM as a professor, they just parameterize it in terms of career, which is a vague word and can suitably mean any number of things for any person. And then they also do, I think, a decent job of highlighting the different barriers to progression that people might face at different phases in their career. Now, this is by no means exhaustive, but they do cover a good deal of things. And I don't have time to even cover all of these, but I will talk in some detail about the ideas of flawed meritocracy and also about how stereotypes, bias, and discrimination impact Black folks in STEM, and specifically how those lead to a lack of role models and lack of mentors for marginalized people in STEM. So let's start with this idea of the flawed meritocracy. There are probably countless examples of this in academia, where the idea is the most deserved people get the most success, but exactly how we measure deservedness is flawed. And something that's kind of adjacent to my career phase as a graduate student is the GRE and physics GRE. So GRE stands for Graduate Record Examination, and these are standardized tests that are usually required or traditionally have been required to apply to physics and astronomy graduate programs in the United States. The general GRE is designed to quantifiably measure your verbal reasoning, quantitative reasoning, and analytical writing. And then the physics test is designed to measure understanding of foundational physical principles. And they do that by asking you many multiple choice questions like this one on the right. And typically you need to average answering more than like 1 a minute to stay on pace. So what these are designed to do is objectively measure aptitude for graduate admissions. And to talk a little bit more about that, I went ahead and went to the GRE website and looked at their guide that they have for admissions committees for applying these scores and using them in application process. And I specifically pulled out these 2 quotes. They say, "The scores support institutions' efforts to identify which applicants are academically prepared for graduate level study." They also say the scores provide a common objective measure to help programs compare students from different backgrounds. So they're saying 2 things here. They say that your success on the GRE should predict your success in graduate school. So the idea is if you do better on the GRE, you're probably having a higher probability of completing your PhD or having a high graduate school GPA or some other metric. They also say that this is a level playing field. So the idea here is you have different students from different backgrounds coming from different universities, different programs, different majors, different socioeconomic backgrounds. But this test is standardized, so it should be an objective measure of who is prepared and has the aptitude for graduate school. But unfortunately, research shows us that this isn't the case. So we can look at a recent study by Miller et al. In 2019, and we can see that the GREs don't really predict what they claim to. So here on our y-axis, we have PhD completion probability, so the probability that you'll finish your degree in grad school. And then our x-axis here, we have different metrics. So right here, we have our quantitative score in the GRE, our verbal score in the GRE, and our physics GRE score. And then on the left, we have undergraduate GPA. So what we would expect if the GRE predicted graduate school success is a positive correlation, meaning people with lower GRE scores would have lower PhD completion probability, and people with higher scores would have higher PhD completion probability. But what we actually see is a weak trend, if anything, and probably a flat trend in most cases. So what that means is people who score poorly on the GRE aren't any more likely to succeed or fail at grad school than people who score highly. So the GRE isn't doing a great job of predicting how well you'll do in grad school. But if we dig a little bit deeper, it gets more insidious than this. So what we are looking at here is the distribution of physics GRE scores. So we're looking at what fraction of test takers did better than a certain score. And this is broken up by gender and also by race. And we can see here that Hispanic and Black test takers tend to do worse than white and Asian test takers. And so, coupled with the previous fact, what this is telling us is that not only does the GRE not predict graduate school success reliably, but it also is putting Black and Hispanic students at a disadvantage. So they're scoring lower. That's not a reflection of their aptitude for grad school because the GRE isn't good at predicting things. But because they're scoring lower and because these are a factor of admissions, they're being put at a disadvantage. So there is a silver lining to this. If you're on Twitter, you might have seen the hashtag Brexit, which is, a play on words for Brexit. And it's gaining steam. So basically, more programs in physics and astronomy in the United States are making GRE score submission optional or not accepted. So actually, the majority of schools now do not require you to submit your physics GRE score to apply to their program. It's not quite at the same level for the general GRE, but that's usually because of bureaucracy at higher levels involved with like grad schools and universities. But things are improving. And I should note that this does not include temporary changes to 2021 policy because of the COVID-19 pandemic, which has caused, economic and health crises. So some universities have rolled back their requirement for this year, but haven't made decisions for future years. So moving on from this false meritocracy, we can also see that Black folks will face discrimination in the workplace and in the classroom. But a key caveat here is that not everyone seems to see it. So I'm going to present another study here. And what these scientists did with this study is they came up with a number of statements. And these statements are commonly cited reasons that Black and Hispanic folks are underrepresented in STEM jobs. And what they did is they presented these statements to some scientists and asked them if they agree or disagree with that statement. And then they broke up the number of scientists that agreed or disagreed by race. And so I'm going to highlight one specific statement. That specific statement says that Black and Hispanic folks are underrepresented in STEM because they face discrimination in recruitment, hiring, and promotions. And this one is especially egregious because we can see that 27% of white folks agreed with this statement compared to about 72% of Black folks. So that's about 2.5 times more Black respondents saying that discrimination is a major component in this lack of representation. And it's not just perception. We can dig further and quantify discrimination in another way. So in another study in 2019, Eden et al. Crafted a number of CVs. So you can think of these as resumes. And they also assembled some simulated hiring committees. And they gave these CVs to those hiring committees and asked them to rate the, pretend applicants. Now, all these CVs amongst the different hiring committees were the same. Same content, same qualifications, same strengths and weaknesses. But what they did was change the name at the top of the CV. And they changed this name to names that people would usually identify with a white person, with a Black person, with an Asian person, and with a Latinx person. And otherwise, everything else was the same. And what they found was that those CVs with typically Black or Latinx names were rated on average 1 point lower than those CVs that had a typically white or Asian name. Again, the content of the CVs was exactly the same. They also found that reviewers were more likely to reward arguable strengths for white and Asian applicants, but more likely to punish arguable weaknesses for Black and Latinx applicants, despite the fact that among the different simulated hiring committees, that all these CVs had the same strengths and weaknesses. So this is a real quantifiable phenomena, and people are doing this perhaps subconsciously, perhaps consciously. And then one more factor that also factors into this lack of representation is microaggressions in academia and in the workplace. So if you haven't heard this term before, I have this definition here from Su et al., which I think defines it quite nicely. They say racial microaggressions are brief and commonplace indignities, whether intentional or unintentional, that communicate hostile, derogatory, or negative racial slights and insults towards people of color. And I think one of the important things about this definition to emphasize is that these microaggressions can be intentional or unintentional. They can also be conscious or unconscious. So people might not know they're doing this, even though they are being aggressive. And what Su et al. Do is they proceed to compile some examples of these types of microaggressions and compile the text of the microaggression, but also the message it's sending. And what the folks behind Astrobytes did is they annotated this figure and replaced some words so that it resonates more with a classroom setting in academia than with the therapeutic setting that the study originally studied. So for example, one microaggression might go along the lines of a faculty or TA member asking a Black or Latino student, "Do you think you're ready for college?" And in the mind of the person saying this, this might be, a normal thing to ask. They're asking, college is a big step. Do you think like you've taken the necessary steps to prepare for it? And they might mean well, but the message that is sent is it's unusual for people of color to succeed. And sure, they didn't mean to insult this person, but that's the signaling that was sent. And we also see a lot of this in relation to the idea of color blindness. So we might have someone say, a student of color expresses concern discussing racial issues with anyone, so say their advisor. And that person replies with, "When I see you, I don't see color." And what the person is trying to say is, I see everyone as an equal. But what the message is that received, what the message that is received says is your racial experiences aren't valid. So they're saying race and culture aren't important variables in your life. But as we've seen from these previous data, this isn't really the case. Like Black folks, for example, are severely underrepresented in STEM, and that's because of the fact that there is racial stigma against them. So these are important variables, and mitigating them with these microaggressions can be part of the thing that drives people out of the field. So the lesson here is that impact is greater than intent. It doesn't matter if what you're saying is well intended. What does matter is the effect of what you're saying. So I know that was a lot of information and we only touched on some things on a surface level, but I want to finish with some key takeaways. And those takeaways are Black students and scientists are severely underrepresented in STEM. And this underrepresentation is solely the product of racist policy and thought, and not because of any supposed cultural differences or inferiority inferred. Discrimination is built into opportunities for career advancement, and discrimination is faced every day by people of color and by Black folks in the workplace and in the classroom. So what can we do about this? Obviously, we won't be able to solve racism overnight, but what we can do is educate ourselves on these issues because they're nuanced and frankly, we don't talk about them a lot. So developing the vocabulary to talk about these issues is in itself a process. We can also listen to Black folks and try to understand their experiences. And when we hear those experiences, and if they don't agree with our experience, instead of being defensive, we should try to lead with empathy and understand that our experiences won't necessarily be the same, but that doesn't mean theirs are any less valid. We can advocate for Black students and dismantle systems of gatekeeping. So there are all sorts of systems of gatekeeping in academia. But for example, one we covered was the idea of the false meritocracy with the GRE. And then we can push leadership to speak up and enact change. Leaders in departments and bosses are ultimately the ones with power, and we should hold them accountable to that power. They have the power to enact change and fix systems of oppression and racism, and we should hold them to that. And then lastly, I just want to make a plug for Astrobytes Black and Astro series. If you just Google that phrase, Astrobytes Black and Astro, you'll see all their articles where they cover a lot of this stuff in more detail and have citations for you to read further and develop your vocabulary and understanding of these topics. So yeah, with that, I will take questions.
All right, thank you. So again, if you have any questions, please feel free to type them in the chat and we can ask Michael here. So we've got one question here, and speaking of microaggressions, I believe I mispronounced your name, it's Angel. What was the reason for the peak number of women identified as Asian earning physics degrees in the US back in the mid-90s? This is in one of the earlier slides that you had shown. Do we know what exactly had caused that?
I actually don't know. I should have looked into it, but my guess is it could have been any number of political or cultural reasons. It's possible there may have just been a shift in the situation with visas, is one piece of speculation for me, but I don't know.
Okay, fair enough. Like, there's a very broad topic to
Yeah.
ask questions on. So what do you think, like in your opinion, is kind of the low-hanging fruit that you can go after right away to try to like increase the number of minorities in STEM? Not necessarily the be all solve all problem, but just what's one simple step we can take?
Yeah, so I'm going to actually step aside and make one quick comment, and that's that we shouldn't just be looking for representation. We should also be looking for representation and equity. If we don't make our field itself a better place for people of color to be, but just improve their representation, then all we're doing is leading to more suffering. So diversity needs to be accompanied by equity. But stepping back to answer your question, low-hanging fruit, at least in the realm of academia for me, is reforming some admissions practices and reforming hiring practices to maybe deal with some of this unconscious bias and some of this false meritocracy. So phasing out the physics GRE and implementing other non-cognitive measures of success. Another big issue I know at admissions is that recommendation letters can often include language that unwittingly can be discriminatory and can influence negatively reviewers' thoughts of the applicant based on things like gender and race. And so looking at how recommendation letters are done and whether or not we should perhaps strip identifying information from recommendation letters is, I think, another direction that could be fruitful.
I think in a kind of a relevant or tangential topic, I know for Hubble proposals, for instance, if you the non-astronomers, if you want to observe something with the Hubble Space Telescope, you have to submit a proposal. They review it. If they like it, they give you time on the telescope. If not, one thing they have started to change is to make it completely anonymous. So kind of like we were saying, to strip away all identifying information. And I believe, like from what I had seen a year or two ago, early results seem to indicate that they are starting to get at least more women accepted for these proposals. So it does seem like making things anonymous is at least incrementally increasing the amount of representation that you get in these accepted proposals. So one thing I know that Penn State has, and I think a few other universities also have now, is something called TMEA, which I know that you are a part of. So I was wondering if you could just tell us a little bit about TMEA, what it is, what it stands for, and what y'all do at the university.
Yeah, so to me is an acronym, it stands for Toward a More Inclusive Astronomy, and it's largely a student-led group that was started in Penn State before my time by some awesome grad students that recently moved on from the university. But it's kept going and has started up at some other universities and astronomy departments. And basically what we do is have a discussion space where we have some usually articles and reading about the experiences of marginalized and underrepresented people in astronomy, and basically do what I said before and like lead with empathy. And it's largely an exercise in empathy and understanding different perspectives in astronomy and from our own. And then recently, something we've also been experimenting with is starting an anti-racist book club. So that was spearheaded by another leader of TMEA. And what we've been doing is reading Ibram X. Kendi's How to Be an Anti-Racist, which has been on the top of many anti-racist reading lists recently. And we've just been discussing that week by week.
Okay. This is, again, kind of stretching what your topic was, but you mentioned, GRE is it can be very dependent on race and gender. Do we have similar studies about the SATs and ACTs and how those can affect people of color?
I am not up to date on those studies, and frankly, I'm not an expert in the GRE ones, to be honest. But I mean, I would imagine that they face many of the same issues that any other standardized test takes or has. And the issues there are that people from more privileged socioeconomic backgrounds are going to do better on average. And that's because they, for example, just as one example, can afford things like test prep for like thousands of dollars. But for other people, just registering for the test itself is a huge expense. So I would imagine that these same issues that are present in the GRE are present at other levels with standardized tests, be it the MCAT, the SAT, LSAT.
Yeah, you touched on it right there, but man, applying to grad school is expensive, right? The GREs, the admissions fees, you got to pay like $30 or so to apply to every school, so it really can filter out a lot of people there. So do you think then that we are seeing a very slow trend of kind of maybe younger people who are being a little bit more progressive in their views, getting into astronomy, maybe pushing this a little bit more. Do you see progress being made, I guess, in astronomy and in the sciences like this?
I mean, yes, I do. Although I will admit I can get impatient and I wish that progress were faster at times, just because of, you know, the nature of bureaucracy and committee meetings. But I mean, this in itself is a bright point because, you know, young people are pushing change, but also at times young people have complained about this because young people, early career scientists, are the ones who are having to push the change because they're the ones with the, you know, more progressive views, I guess is one way to put it. And the early career scientists are the ones with the, you know, the least job security and least power. So it's, you know, a thing that I think bodes well for the future, but also can be very frustrating.
Okay. And then you had mentioned removing fees and using non-cognitive indicators as indicators of success. Could you kind of mention what some of those might be?
Yeah, so the idea there is that instead of relying on flawed numerical metrics like you know, your GRE score, your physics GRE score, your undergraduate GPA, which as we saw aren't very standardized and, you know, can be tools of discrimination, you instead frame questions in your application that look for positive research qualities. So for things like perseverance and the ability to like ask questions on your own and follow up on those questions. And that's a harder thing to do. Typically, I think most of those things are looked for in letters of recommendation, but I think they're things that can also just be asked directly of the applicant instead of, you know, alluded to in your statement of application or asking for letters of rec.
Okay. All right. Well, thank you again, Michael. This is, I think, a very important topic, and I'm happy that we could touch on it. So thank you for researching and giving us talk. We really appreciate you coming out here.
Yep, of course.
All right. So now we are going to get back to our trivia answers and announce our winner, as well as the answers to all our questions. Realize this one may have been a little bit tough. Do apologize for that. Hopefully you learned some astronomy on the way. So I'll go ahead and hand this off to Arvin, and he can tell us who won trivia.
Sure. Actually, real quick before I get to that, I want to plug a book. So this book that I recently read, Whistling Vivaldi, it talks about stereotypes a lot, and it actually has answers to some of the questions that people in the audience were asking, and that Michael, that you asked that we didn't really cover in this talk here. And I don't know, I think it's a really good overview of a lot of how academia and academic things are influenced by stereotypes. So yeah, now let me get back to Zoom. Again, remembering how to use this computer that is not mine.
It's a Mac, right? You have a PC, so there's some
It is a Mac, yeah. Nothing wrong with Macs. Okay, I'm on the wrong slide. Let me get back there. Okay, so here we are. All right, so first I'll say that, yeah, this was a hard trivia round. If you didn't do well, don't feel bad. I think the average score was maybe 7 out of 15. I guess I didn't realize how hard it was when I was making it, but in hindsight, I probably wouldn't have gotten a lot of these myself if I didn't know the answers ahead of time. So the first one was the Crab pulsar. Actually, I think most of you got this one correct. This was taken in the X-ray by the Chandra X-ray telescope. Number 2 was supernova 1987A. This was definitely not one of the first images taken of it, because early on it was followed up almost immediately by ground-based telescopes as soon as they could get their eyes on it when it was discovered. But later on, the Hubble Space Telescope took a visible light image of this guy. That is what you guys see right here. Number 3, the M87 black hole. So I think I already showed the answer, but this was taken in the radio by the Event Horizon Telescope. As Michael said earlier, astronomers have special wavelength range that we talk about called the millimeter. Normally when people talk about the electromagnetic spectrum, there's the microwave and then the radio at longer wavelengths, but sort of on the border of those two, there's millimeter wavelengths. And that's where this was taken. This is about at 1 millimeter. This is the Cat's Eye Nebula. This is another visible light image. Number 5 is the Andromeda Galaxy. I think most of you got this one as well. By the red color, you kind of inferred that it was infrared. I did not recolor this one. Venus, this was taken in the radio. The fact that it's 3D probably helped many of you get the answer right here because we're able to map it from a bunch of different surfaces with a telescope using radio waves. Halley's Comet, this was also visible light. This is what, obviously this exactly isn't what you would have seen with your naked eye, but with a telescope, you probably could have seen something similar to this. Jupiter's Aurora here. I recolored this one. The original image was sort of bright blue, but even that was false color because this was taken in the ultraviolet and human eyes can't see ultraviolet. So the bright blue image that you might be more familiar with of this is false color as well. Number 9, this was that galaxy merger, NGC 3808. This one is also a visible wavelength image. 10, our second Venus image. I think many of you thought this was visible, but it's actually taken in the ultraviolet. The visible images of Venus have more of kind of a brownish yellowish color. The Cat's Paw Nebula here, I think most people got this one correct as well. This was the infrared. HL Tauri, I recolored this one. It's normally shown as sort of red and orange because it was taken in the radio at much longer wavelengths. And the only reason we're able to actually resolve a disk like this is by using a technique called interferometry, which is easiest to do at long wavelengths like the radio. NGC 6744, this one looks like it could be visible, but it's actually taken in the ultraviolet. Number 14, I will apologize to those in the audience. So I stated that this was early 90s before I was born. I understand that made some people feel old. I did not mean to do that, but I guess that's how it is. This was taken in the infrared as well. The sun, our last one, a lot of you thought this was X-ray, but many of you also got the correct answer. This was ultraviolet. We don't need to go much shorter than visible wavelengths to see these prominent features that we can't see with our eyes. So tonight's winner was the team Early Heavy Bombardment, a nice take on the phenomena called the Late Heavy Bombardment, which was something that caused a lot of impact craters on things in the inner solar system. So to whoever that winner is, I will send you an email later this week talking about information to send you your trivia prizes. This team had 14 out of 15 questions correct. Pretty impressive given the average scores, but hey, I guess some people are really good at this. I'll also give a shout out to an honorable mention team name. I don't remember your score, but the team that was Saturn's Onion Rings, I think that was my favorite astronomy themed name. Thanks, guys.
All right, thank you, Arvind. So thank you to both of our speakers, Dr. Monroe and Michael Palumbo. This is really awesome Astronomy on Tap. Thank you all for coming out and sticking with us. Those of you in the audience, yeah, as Carol says, I think we all know who Late Heavy Bombardment was. We hope to be back in August, so stick with our YouTube channel. You can find us on Facebook, and we hope to see you back in 1 month. Thank you all for coming out.
Thank you.